Good morning to everyone. I'm Dr. Sumi MS. The name of the course is Electromagnetic Fields and today's lecture topic is Plane Waves in Lossless Medium. On completion, the students will be able to understand the properties of lossless medium of electromagnetic waves and define the attenuation and phase constants of electromagnetic waves. Lossless medium for electromagnetic waves. A lossless medium is a medium with zero conductivity and finite permeability and permittivity. When an electromagnetic wave propagates through a lossless medium, the amplitude of its electric field or magnetic field remains constant throughout the wave propagation in that medium. The properties of the lossless medium affect the speed of propagation and it is reduced by a factor of 1 by root of mu r epsilon r when compared to the same speed of the same wave in the case of vacuum. So here mu r and epsilon r represent relative permeability and relative permittivity of the medium. A lossless medium for electromagnetic waves is a medium with zero conductivity and finite permeability and permittivity. Permeability is given as the product of relative permeability and permeability of free space mu r mu naught, and permittivity is obtained by the product of relative permittivity and permittivity of free space. Consider a plane wave propagating in the y direction with electric and magnetic fields mutually perpendicular to each other and also to the wave propagating. A set of wave equations are used to define these electromagnetic waves, which are expressed in equations 2 and 3 representing the E field and H field. The general solution to the linear homogeneous second order differential equations based on the above two equations can be obtained and is represented in equations 4 and 5, which comprises of both the medium in which the wave is being propagating. From the above equations, we can conclude that other than the field amplitudes E1, E2, H1 and H2, the electromagnetic wave characteristics of the fields are identical. Characteristics of the electromagnetic waves defined by the general field solutions can be determined by investigating the corresponding instantaneous electric or magnetic fields. And considering this, the time domain solution of the wave equation in terms of electric field can be represented as in equation 6. In this equation, alpha is the attenuation constant and beta is the phase constant and omega is the angular velocity of the wave propagation. The attenuation constant is the measure of the attenuation of the amplitude of the fields in the electromagnetic wave propagation, and we can obtain attenuation constant from equation 7. As the wave moves forwards, its phase may undergo variations, and the factor that indicates this phase variation is called as phase constant, which is represented in equation 8. And by substituting the conductivity sigma equal to 0 in the above equations, we can obtain the value of attenuation constant alpha as 0 and the phase constant beta can be given as omega by root of mu epsilon. So equation 9 is the mathematical representation of no attenuation in a lossless medium. When an electromagnetic wave propagates through a lossless medium, the amplitude of its electric or magnetic field remains constant throughout the wave propagation. That is, there is no reduction in the amplitudes of the wave in the course of its wave propagation through such a lossless medium. In this lossless medium, the electromagnetic waves can also be called as a non-decaying waves as there is no reduction in the amplitude of the wave. The phase of the electromagnetic wave changes in the lossless medium and it is influenced by the velocity of the propagating wave, and also it depends on the characteristics of the medium through which the wave is propagated. So equation 10, which gives the relation between the phase constant and the velocity as well as the permeability and permittivity of the medium is represented. This equation shows that as the value of relative permeability and permittivity of the medium increases, there is an increase in the phase constant. The angular velocity of the wave matters when this wave is having phase variations. Now, the effect of a lossless medium on the velocity of the wave propagation has to be considered. and the velocity of wave propagation is given as the ratio between the angular velocity and its phase constant. So equation 11 represents the velocity of the wave propagation, which is the ratio between angular velocity omega and phase constant beta. Since we already know that the value of beta from equation 10, we can rewrite equation 11 as u is equal to 1 by root of mu epsilon, where mu and epsilon are the finite permeability and permittivity of the medium. And from this equation we can see that the properties of the lossless medium affect the speed of propagation, and it is reduced by a factor 1 by root of mu r epsilon r compared to the speed of the electromagnetic wave in vacuum. Quiz questions on plane waves in lossless medium. Describe the properties of lossless medium of electromagnetic waves. What do you mean by attenuation constant? Thank you.